Good morning, everyone. My name is Yasser Shukri. I'm an assistant professor in the University of California, Irvine, where I lead the Resilient Cyber Physical Systems Lab. So let me start by thanking the organizers for giving me this opportunity to share with you some of our research on how we can build a secure, safe, and resilient Internet of Things, especially when IoT is interacting with the physical world. So while IoT is used in multiple applications, so today we are going to my research focus mainly on the cases when IoT is interacting with the physical world, or what people sometimes refer to as cyber physical systems. And just as an example of such systems is the video that you can see on the slides right now, where this is an example of a fully autonomous container terminal in Germany. And as you can see, you have hundreds and thousands of sensors and actuators interacting together through a large-scale Internet of Things system. All the information collected from multiple sensors are organized together in order to facilitate the autonomous operation of this terminal. As you can see, all loading, unloading, all the driving of these different packages are happening autonomously inside this very large scale cyber physical system or IoT. And this interaction between the cyber world and the physical world can open several questions and challenges that we as engineers need to answer. And the first challenge is what happens when there is some bad actor in the system that is trying to use this interaction between the cyber and the physical world in order to force this IoT system to take harmful decisions. So here is, in this example, this luckily didn't happen. This is just part of a Hollywood movie. Nevertheless, one can argue that we are not far away from witnessing such large-scale cyber attacks that can leverage this interaction between the cyber and the physical worlds in order to force harm on the physical side of the system. As you can see here, this is a massive cyber attack that allowed the attacker to control all the physical systems in the IoT system and use it to take wrong decisions that can be of various harm to the system. So the first challenge that we are interested in our group is how we can reason about security problems in these kinds of systems. But even if we forget about the malicious intent and we focus only on having systems that are safe, just designing systems that are safe in the first place can be problematic and challenging in the same time. As you can see in this example, this is a Volvo car where they were testing the autonomous braking functionality. So this is a this was supposed to be the press release of this new technology. And as you can see here, the press release went completely wrong. And you see now he's trying to apologize for this embarrassing moment. But this highlights the second challenge of building such systems, which are safety systems. One can argue that the one in the example I just showed for the Volvo car is not a large-scale IoT, but even just a very small system, just trying to build a system, make sure it is safe because of this interaction between the cyber and the physical world. This can be a very challenging problem. Moreover, just designing these systems in the very first place can be challenging as well. So if we forget about safety and security, just making these systems work in the first place can be challenging. As you can see here, this is an example from Boston Dynamics, which one can argue one of the best robots in the world, and just building systems that can work in the first case can be challenging and needs a lot of engineering work. And we argue that in order to reason about these three problems, which are security, safety, and designing controllers for these cyber physical systems and IoTs, we need design tools that can help automating this process. So the vision that that we have in our research group is how we can build design tools that can take and input some description of these larger scale IoT systems that interact with the physical systems, and how we can build these design tools that can reason about security, safety, and even automate parts of the design of these larger scale systems. So let me start with security, and in particular, I'm going to focus on one particular security threat that we call sensor attacks. So why we focus on sensor attacks? So if you look into any IoT system where you have multiple sensors, collect some information about the physical world. These sensor measurements get distributed inside your IoT until it goes to the decision-making units, which then take some actions and apply to the physical world. And as you can see here, the sensor is the input to any of those systems. It is the eyes by which the IoT system can see the world around it. And we ask the question, how can a malicious actor can use these sensors and can inject attacks on these sensors such that it can influence the decision making taken by these systems in order to make it take wrong decisions that can be harmful. So today I'm going to discuss three different versions of this particular attack. First, I'm going to discuss what we call as false data injection attacks. Then we are going to make it a little bit more complex and add civil attacks on top of it. Then we're going to make it even more complex and add some privacy concern on top of security attacks. So false data injection attacks especially in the sensors arena, refer to how we can maliciously corrupt the sensor measurements in order to report something that doesn't happen in the actual physical world, but report something that is fake without the system being able to detect it. So to give you just an overview of how most of these attacks work, so I think this video is very representative. So here, as you can see in this video, these guys are trying to attack a particular system. So here we don't have sensors, but we have an actual guard. So think of this guard as the sensors of the inside the system that is trying to recognize what is happening around him in the physical world. And what these guys did is they used a device to shield the sensing of this guard, which is his eyesight, from what happens in the physical system, and then use the same device to inject something that is not actually there in the physical system. So we use the same kind of strategy to attack sensors in automobiles. So if you go to your car, just look behind the wheels, you'll be able to see the anti-lock braking system sensors. So these sensors are used to measure the speed of the wheel, and these measurements then go to your anti-lock braking system controller, which uses this information in order to apply brakes on different wheels inside your car to stabilize the system. And what we did is exactly similar to what I showed you in the video, where we used some some magnetic sensors and actuators. So before I go there, let me just tell you a little bit of how this sensor work. So this sensor, so this sensor here, you can see there is a magnetic sensor out here, which is the wheel speed sensor. So this is fixed and attached to your body of the car. And then you have here a tone wheel that rotates in front of a permanent magnet. So when the tone wheel rotates, what will happen is you'll have some magnetic field oscillating around the sensor, and the frequency of this oscillating magnetic field is equivalent to the speed of rotation of your wheel. Now your sensor takes this magnetic field, turns it into an electrical signal that then pushed into your ABS controller. And what we did out here is we designed this set of magnetic sensors and actuators that can measure the magnetic field around the sensor. And then we use an actuator to generate a magnetic field with an inverse sign So it cancels out the magnetic field around this sensor, and then use extra actuators to put a new magnetic field around the sensor with a completely different frequency that does not correspond to the actual wheel speed of the car. So here we built a small test bed with some actual sensors from Mazda car. And as you can see here in this result, so the red curve out here is the actual wheel speed without any attack. The black dotted line is the attacker intention. This is what the attacker would like the sensor to read. And as you can see, because of the attacking mechanism that I just described, the sensor under attack is actually more or less reading what the attacker intention or what the attacker signal would like it to read. Now, we wanted to implement this attack on a real car. So although my PhD advisor at that time, Paulo Taboada, volunteered his car, for obvious reasons, we couldn't find a driver to ride a car with an anti-lock braking system being under attack. So nevertheless, we reached out to our collaborators in the industry, and here we are using one of their simulators just to test the consequences of this attack. So what you see here in the first part of this video is the normal anti-lock braking system behavior. You see some ice, you apply the brakes, that's what you expect from the anti-lock braking system. But now let's attack only one of the wheels inside the system, and same scenario, same controller, same everything. That is what is going to happen. In particular, we were attacking this sensor out here for, corresponding to this wheel, reporting wheel speed that is smaller than the actual speed. And because we are reporting smaller velocity, wheel speed than the actual physical one, the anti-lock braking system decided not to apply brakes on this wheel while it is actually rotating very fast, but the ABS computer was not able to recognize this because of the attack on the sensors. And he started to apply brakes on all the other wheels, resulting into the behavior that you just witnessed right now. So this is not the only attack that was reported in the literature. So other researchers have used similar ideas to implement attacks on pacemakers, as well as sensors inside your drones, especially gyroscopic sensors, which are very sensitive to acoustic signals. And the message behind all these attacks out here is traditional information security offers no defense for this against these types of attacks. And this is a result because these attacks happens in the physical arena before even the sensor measures the signal, and before the signal goes to the analog to digital converter and then goes to your classical cryptographic or information theoretic firewalls. So the source of the information itself has been corrupted even before it goes to the cyber world. And that's why traditional information security like firewalls, cryptography, and so on cannot provide any defense against these kinds of attacks. So now let's put the hat of a defender and try to see how we can reason about these attacks, and how can we design systems that are secure and resilient against these kinds of attacks. So there are multiple defenses. One of them is how we can build better sensors that can be more resilient. We have done some work in this side, but what I would like to discuss today is more of a system level design. So if you have a large scale system with multiple sensors and actuators, here is just an example of a car. It can be a large IoT system like a power grid. It can be a traffic system. At the end, you have multiple sensors. These sensors are heterogeneous. Each sensor is measuring different aspects of the physical system. So typically what we do is you collect all this sensor information, you try to do sensor fusion, you try to do some estimation of the state of the physical system, and then you feed this information to your control algorithm, which closes the loop and take decisions in order to lead the system to take certain decisions that maximize its performance, for example. Now we ask the question, what if that some of those sensors are under malicious attack? We don't know which sensors are under malicious attack, but we know that maybe some of them is being hijacked. And we would like to design a secure state estimator. We'd like to design a sensor fusion algorithm that tries to use all the information from the entire system in order to know which sensors are lying about their information and which sensors are reporting actual measurements from the system. So to be more specific, the threat model is as follows. So you have P sensors in total inside your system. S of them is under malicious attack. And by attack here, I'm referring to any kind of an attack. It can be sensor spoofing, like the one I showed in the anti-lock braking system example. It can be someone sitting on the communication channel between the sensors and the controllers. It can be a software virus. It can be anything. We don't know how the attacker is going to attack the system. And the attacker is free to corrupt either all the sensors that are compromised. He can attack some of them, he can attack none of them, but at least the maximum number of sensors that can he attack is this S out here, okay? And the attack can be arbitrary. We have no idea what is the bounds of the attack. We don't know any stochastic model about the attack. The attacker can do whatever he wants to do within these S sensors out here. And the key idea is how we can exploit the physics of the system in order to build some sort of redundancy. Let me give you a simple example. Suppose you have an electrical motor and you have a sensor that measures the speed of this motor, and you have another sensor that measures the electrical current going to this motor. From physics, we know the relation between electrical current and the expected motor speed. So although I have two sensors that are heterogeneous, but these two sensors are connected together or coupled together through physics. So physics allows us to increase the redundancy of the information that we got from the sensors. Even these sensors are very heterogeneous and they are not measuring the same exact state of the physical system, but our understanding of physics helps us to build better defense mechanism. The question is how we can use this simple idea, but how we can scale it, how we can operate in real time, especially that this problem of secure state estimation is proven to be an NP-hard problem. The naive solution to this secure state estimation problem is to take all different combinations of sensors and compare them together until you find a subset that don't agree together, and then you say, okay, this subset of sensors is under attack. Of course, such a combinatorial aspect for which you are trying to try all different combinations of sensors does not scale well, and that's why we need novel algorithms that can perform this secure state estimation at real time for large scale systems. I'll not go through the details, but I would like to show you some numerical examples. So here is different approaches that were proposed in the literature. So here in this example, we have a power grid. We have 500 sensors in the power grid, 100 of them being under attack. So the first approach is to do a brute force search, like what I just explained before, where you take all combinations of sensors and you try to check all of them and try to see which one of them will fail some sanity check. Of course, for 500 sensors with 100 of them being under attack, you have a huge number of combinations, and this approach timed out after 7 hours without giving the right answer. You can use mixed integer programming, which for this particular case takes around 1.5 hours. You can use satisfiability solvers like SMT solvers, which have been used in the literature of computer science to solve combinatorial problems. Again, this timed out in our case after 3 hours. Here, using the technique that we proposed, which combines some ideas from satisfiability solvers with some ideas from convex programming, which is used heavily for signal processing, we were able to push down the computation time into 15 seconds. And this is without any heuristics, without any relaxation, but we are actually solving the exact problem. So let me show you another example. Here, let me again from the beginning. So here we have this quadrotor out here under sensor attack, where we are attacking the measurements from the sensor measuring the position in the Z direction. And as you can see, the jitter in the quadrotor, until at this point we increase the attack vector, and this is what just happened. Now here, using the same algorithm that we described, that we call satisfiability modulo convex programming, with the same exact scenario. Now, as you can see, the quadrotor flight is much smooth, although it is under the same kind of an attack, until at this point of time will increase the attack vector. And as you can see, we can detect the attack and we can bring back the quadrotor into safety. And again, the main technique out there is how we can use the physics of the quadrotor in order to increase the redundancy in the information we get, so that we can compare measurements we got from different sensors in order to detect which sensors are under attack and which are not. But the problem is combinatorial, and usually the challenge is how we can do this in an efficient way. So this is the false data injection attack, which is attacking some of the sensors, forcing them to report wrong information. Now let's make the problem a little bit complex and add to it another scenario, which we call Sybil attacks. So consider this smart traffic system, where you have an IoT system inside which each of the cars is reporting its position and velocity to the cloud. And then you have an IoT controller that routes the cars inside the system, inside the traffic system, in order to optimize some throughput, for example. So now assume you have this bad actor out here, this malicious red car out here, that is not reporting its correct position and velocity, but moreover is reporting the existence of some cars that does not exist on the highway. So this yellow car out here is actually a fake car, but the red car, when it is reporting to the IoT system, it says my position is at this XY position, and I see a car behind me. And then it takes the identity of the car behind it, and then it can report the existence of this car, and then it can start adding more and more fake or ghost cars inside the highway, until it wins or dominates the information that is reported to the system. And because of that, the IoT controller will think that there is a lot of congestion on the highway, and then will start routing the actual cars into the sideways, creating a real congestion on the sideways while the highway is actually free. But because of all this fake information that is reported on the highway, the IoT controller took the wrong decisions that can harm the system instead of increasing its performance. So here we have two types of attacks. The first one is this false data injection, in which the red car is generating or reporting incorrect information or maliciously corrupted information. But also we have this Sybil attack, in which cars that does not physically exist are being reported on the system. So these ghost or Sybil cars can be easily generated until you can win the majority of the information inside the system. And the objective is, again, how we can use all the information from the reported from the cars, along with information reported from the traffic system. So we have these loop sensors inside the traffic system. These sensors usually are very noisy. They are not accurate enough. They are sparsely distributed across the system. We don't have many of those, but yet they report some information that can be used in order to enhance the resilience and the security of the system. So we'd like to collect all this information in order to do some traffic estimation, and then we use this traffic estimation, pass it to a routing algorithm that routes the cars inside the system. And of course, the challenge how we can build now a secure traffic estimation system or secure traffic estimation algorithm that can identify which cars are reporting wrong information and which cars are not reporting the right information. Again, the general idea of how we can use physics in order to enhance the security and the resilience of the system. So a lot of research and literature have focused on how we can use this information from loop sensors and propagate them along the highway and the sideways in order to generate some estimates of how the traffic velocity and traffic congestion is there, and then we can compare them with what is reported by the actual cars and between different combinations of cars until we can find exactly which cars are reporting wrong information, which cars does not exist, and so on. How we can use these physics in order to tighten tighten the space or tighten the possibilities from which the attacker can launch his attack. So here is one case study we did on data set from the Bologna Ringway data set. So this data set reports the typical traffic between 8 and 9 a.m. The rush hour in the city of Bologna in Italy. And then we use this simulator called the Sumo simulator in order to simulate these cars out here and then start injecting some malicious cars on the system and see what will happen in the traffic routing algorithm. So here is some results. So as you can see here, the red one is when you have the IoT system without any security. So what we are reporting here is the average travel duration for the cars inside this traffic system across time from 8 in the morning until almost 8:30 in the morning. And as you can see here, when you have an attack, the average travel time started to increase because the attacker is creating this fake congestion on the ringway inside the Bologna, forcing most of the cars to go inside the city, creating real congestion inside the city. While with our system simulated, of course, inside this simulator, we can push down the average travel time all the way to almost its normal behavior. So the second figure is with a much stronger attack, where it almost where we put a lot of fake cars that pushed most of the cars inside the sideways, capping the system into its maximum capacity in terms of traffic. Now all the traffic is jammed inside the city, but now thanks again to the same algorithm that we developed, we can push that average travel time back down to almost its normal behavior. So this is an example of when we have these kinds of attacks, when we have false data injection, some of sensors are malicious, and on top of it, we have these fake sensors that are reporting malicious sensors, malicious information as well, but they don't physically exist in the system. Now let's add on top of this some privacy concerns from different sensors. So the setup out here is you have the sensors are collected from different sources, but these two sources, but these different sources don't trust each other, and they don't want to share their information together. For example, suppose someone heard some event in his neighborhood, like a gunshot, for example. He would like to report it to the police, but he don't want the police to use this information to track his position, for example. So there is this trust issue between the different sensors. And on top of this, we have some sensors that are malicious and they are reporting incorrect information. And then now the challenge is how we can identify those bad actors without, while still having strong privacy consideration of privacy guarantees. So the threat model is we will just focus on the localization problem, where each sensor knows its position, XY position, and would like to report the distance to a certain event. So each sensor would like to report its XY position and this D out here. And all these sensors will go to an aggregator, which is going to aggregate this information and then give it to someone that is interested in the final answer. This query node can be one of these sensors, or it can be another different entity in the system. For example, these can be multiple people reporting a gunshot, and this can be the police station, for example. And the objective is we would like to compute this XY position of this target out here, while ensuring the privacy of all the sensors. To be a little bit more specific, from the privacy point of view, we would like to make sure that so we have M sensors in total inside the system. We'd like to make sure if M-1 of these sensors are dishonest and they are colluding together by sharing their information between them, there is no way they can retrieve the information that is generated by the last sensor. So this is, we call privacy against sensor collation. So any a sensor that can collude with up to M-1 other sensors cannot leak the information about the last one. Similarly, we would like to make sure that if M-1 of the sensors is colluding with the aggregator, they still cannot get the information or reverse engineer the information that was sent by this last sensor SM out here. And on top of it, some of those sensors out here are malicious. They are reporting incorrect information, and we would like to make sure that the aggregator is computing the right X and Y of this event out here, regardless of this malicious attack. And the technique we used is using ideas from computations over encrypted messages. So one direct application of this literature of using what is known as fully homomorphic encryption that allows you to encrypt data and then do some processing over the encrypted data without being able to know the actual information. And then after you do all the computations, at the end, someone have the key to decrypt the data and get the final answer. So just applying this technique out here. So the first step is each of those sensors or observers is going to encrypt his data and then send it to the aggregator. The aggregator does not have the key to decrypt the data, but yet we can use this fully homomorphic encryption in order to do the computation, which is just a bunch of multiplications and additions and so on, just computing some, performing some linear algebra computations over the encrypted data. And after he do all these computations, he will send the final encrypted output to the query, which have now the key to decrypt it and get the final result. So using the off-the-shelf algorithms for fully homomorphic encryption will result into computing this in this scenario that it will take more than 11.7 hours just to, when you have 5 sensors and you're doing all these computations out there. This is because these computations over encrypted data is usually very time consuming, and especially the multiplication can take some of time. While people in cryptography have been focusing on how we can build better fully homomorphic encryption, what we have focused on right here is a little bit different. How we can change the algorithm to that is trying to compute the aggregation, that's trying to do the sensor fusion, how we can change the algorithm, the signal processing algorithm itself, such that we can use a much better or a much better in terms of complexity, of time complexity, homomorphic algorithms that can lead to better computation time. In particular, instead of each sensor reporting its XY position and distance to the event, they can instead report this polyhedra instead, which can be represented by a certain matrix and one vector. So the matrix corresponds to the shape of the polyhedra, while the vector corresponds to how far each of those facets are from each of these faces away from the center. And we showed that the computations that are done on the aggregation over the aggregator over this signal processing algorithm that we propose can lend itself to use a much low-weight cryptographic algorithm called partial homomorphic algorithms that can push the execution down all the way to 103 milliseconds. So just by playing around with the algorithm itself, you can support or you can use better cryptographic algorithms out there. And we can do the same trick when we have multiple sensors being reporting incorrect information. Now, similar to the false data injection attack, you can try to do different combinations of sensors until you find a set of sensors that are attack-free. And we can show that with this algorithm, we guarantee that even if n-1 sensors are colluding together, they cannot reveal the last one, even if the information from the last one. If you have n-1 sensors colluding with the aggregator, they still cannot retrieve the information of the last one. And if you have less than this number of sensors being under attack, then the system or our algorithm can still identify the right position of the event that we're trying to localize. So, but this comes with a slight cost, where the mean square error of the localization that we do is slightly higher than if you use the original, the classical least squares localization out here, because of the discretized, because of the idea of using polyhedras, usually add a little bit of error around this circle. So when we do localization with this geometrical shape, you will end up having a little bit of an error out here. So these are three different types of attacks that can happen in IoT, especially when they are interacting with physical systems. And just to summarize, in the first one, So in the first one, which is the false data injection attacks, we were able to identify which sensors are good, which sensors are bad, and use this for estimation of the system, the state of the physical system. And then we added the Sybil attack on top of it, and we showed the example of this traffic system. And then we added privacy concerns on top of it, which is in this localization example out here. So now let's move to a different problem, which is safety. And this is more related to the current use of machine learning and neural networks inside these IoT and cyber physical systems. So while machine learning have been doing a great job lately, yet in a lot of scenarios, still they don't guarantee the safety of the system. So here is an example of the new auto summon inside Tesla cars. And as you can see here, there is no object that is obscuring the vision between the Tesla car and this moving guy out here, yet the Tesla car couldn't identify this pedestrian and was almost going to hit him. Here is another scenario when the Tesla car failed to stop in the top sign, was leading to a near accident in that other video. So while machine learning is very useful, it has a lot of impressive results recently, still the question is, when we use this machine learning to control physical systems, how we can guarantee that the final design system have some safety properties. So this is the classical way of training a neural network. You have some training and evaluation data, and then you use your best training algorithm or machine learning algorithm in order to try to optimize and find these neural network weights. However, we argue that for physical systems, we have a lot of more information, In particular, for most of the physical systems, we have some imprecise models coming from mechanics and physics and so on that provide a lot of information that can be leveraged in order to have a better process to designing neural networks. So given this imprecise model of the system, the first question we ask, can we design a neural network architecture that is guaranteed to be correct? So if you are familiar with the current literature of in designing machine learning, usually you have to start with some neural network architecture where the architecture means the number of layers inside the neural network, the number of nodes or neurons inside the neural network. And you try to train it, and then it doesn't work. You have to change it. It doesn't work. You make your neural network bigger or smaller. You add more neurons and so on until you figure out one that works for your system. So instead of this iterative procedure, what we are interested in is, given the imprecise model of the system, how we can directly find a neural network architecture that is guaranteed to be correct, even before you have any access to any data, just from the understanding of the physics as well as the objective of the system. For example, if you'd like to your system to just avoid obstacles, you have some specification written in some formal language, like temporal logics, for example, and we take it with the imprecise model of the system in order to generate this neural network architecture. Once you now do your training, the next question is how you can verify that the neural network that you train is actually satisfying your specification out here. So typically neural network, we do some evaluation or validation using data, but this evaluation and testing is not guaranteed to find all different counterexamples that for which the system is taking the wrong decision. So the next question is how we can build these neural network verification engines that take a neural network, take the imprecise model of the system and specification, and can give you formal guarantee whether the system is guaranteed to work correctly at all times, or it can give you a concrete counterexample saying, when the car is here and it's facing this direction and there is someone out there, the controller is going to take wrong decisions and is going to violate the specification. And this relates to a lot of work that have been done previously in software and hardware verification in the formal verification community. Now the question is how we can leverage it to do verification for neural networks, especially when they are controlling physical systems. Once you find a counterexample, now the question is, can you use this counterexample in order to try to repair the neural network? Instead of retraining the neural network from scratch, can you go ahead and try to just fix parts of the neural network until you get a better neural network? Or if not, can you use this counterexample that is generated as new data and augment it to the data that you have out here in order to retrain the neural network until, and then you iterate out here inside this loop until you get some neural network that is trustworthy, that is guaranteed to work correctly. So again, without going into the details, I would like to show you some results on one of the examples that we have designed. So the question out here is the following. You have your physical system that is controlled by a neural network. This neural network processes camera images and so on in order to close the loop and give control actions back to the system. And we would like to design this small neural network out here. Think of this neural network as a root of trust, that whenever it takes actions from here that is not safe, it is going to correct it to the closest safe action before it goes back to the physical system. Whenever the actions that are generated by the neural network that you trained is safe, this neural network is just going to pass these actions through to control the physical system. And in order to do this, this neural network will need, in addition, some information from the LiDAR sensor. So the original neural network is processing multiple signals like cameras, LiDARs, IMUs, and so on. This one in particular needs information from the LiDAR sensor, because LiDAR can give you always information about how far you are from obstacles. And the question is how we can combine this information to design and this root of trust that is guaranteed to make the whole system safe. So we have proposed different algorithms for how we can do this architecture synthesis, this training, this verification, and so on. We have been actively working in this area for the last 2 to 3 years. So, but I would like just to show directly one example. So here in this example out here, we trained a neural network that is trying to control this robot in order to take the car from its position here till the end of the highway, while avoiding those pedestrians that appears randomly on the highway. And so as you can see here, this is we trained a very poor neural network, as you can see here, because of that jittering. Nevertheless, because of the root of trust network that we designed in this previous slide out here, because thanks to this one out here that we designed and verified and was able to make sure it formally satisfy the system specifications, what you see here is even for a terribly trained neural network, we still can guarantee the safety of the overall system. So even that the original neural network out here, this one that we trained to be very poorly, once you add this one on top of it, the combination of them is still guaranteed, provably guaranteed to be safe. So here is a couple of other examples, again using the same technique on different neural networks that are trained across different data with different parameters and so on. And as you can see here, for all of them, we can guarantee that the system will always be safe, avoiding the obstacles. So here is some comparisons. So what you see here on the left is the neural networks that we trained without adding this extra small neural network that we call root of trust that is formally verified. So this is without this, this root of trust. And what you can see out here is how far, the histogram of how far the car is away from obstacles. And remember, these cars are around 2 meters long. So anything behind this bar out here, it corresponds to an accident. Anything between around here corresponds to near accident cases where the robot was almost about to hit the pedestrians. Now, as you can see, when we added this additional neural network that we call root of trust, you can see the histogram of how far the cars have been pushed all the way, mostly behind this bar out here, where the car is always almost leading to 4 meters away from each of the humans, corresponding here where the average is around 2.5. And as you can see here, there is a lot of accidents. Here we have only one accident that happened out here. Similarly, here you can see more testing where this is the obstacle hit rate. And as you can see, whenever our whenever this root of trust is not there, which is these off conditions, these off rows out here, all of them correspond to a high hitting rate. Whenever our shield this root trust is used, then as you can see here, the number of obstacle hit rate pushed all the way to 0 or around 0.5%. And this is across multiple experiments and so on. And here again, a little bit more results that shows that the obstacle hit rate out here without our root of trust that is formally verified, and here is with the root of trust. This is during training of the neural network, while the neural network itself is still in the training phase, using some data in order to adapt its weights. As you can see here, using this root of trust that we propose and formally verified can even help the training of this algorithm, of these neural networks, as well as help them during execution. So this is just a summary of some of our results on how we can provide safety for deep reinforcement or deep reinforcement learning and machine learning when it is used for controlling physical systems. And just finally, I'll touch base a little bit on some other work that we have done in terms of helping controller designing controllers, especially for when you have multiple physical systems interacting together in order to achieve a certain mission. Again, how we can design algorithms that can help these designing these systems. So what you see on the top left corner out here is one scenario in which you would like to design a system that have multiple quadrotors, and we have a mission in which the quadrotors needs to always one of the quadrotors have to be always inside this corridor. So for example, think of this corridor as these are police quadrotors, and they are trying to patrol this particular area. So the mission says that at least one of these quadrotors have to be here at all times, and everywhere and then this quadrotor needs to go there to this charging station, while this one needs to go here to its charging station. So we have this information about the mission, and we know a little bit of the physics of these quadrotors. And the question is how we can automate the design of these controllers. So the controllers you see out here is automatically generated just from this information. There is no code being written manually. We just give, we have these tools that we have designed, for which you give it the specification in some formal language like temporal logic. And it directly generates for you these kinds of controllers that is guaranteed to satisfy the mission that you are interested in. Similarly, in the one out here again, you have multiple components interacting together, and then we would like to automate the controllers for all these. And instead of manually designing controllers and then verifying them, making sure they work correctly, the question how we can automate the design. And again, we provide different design tools that can help with this process. So let me stop out here. So today I discussed with you some of our effort on how we can design tools that can help in designing security algorithms for sensor attacks. How we can design, how we can have some design tools that can help in analyzing the safety of machine learning when it is used to control physical systems, as well as how we can have design tools and algorithms that can help with the design, automatic synthesis of controller designs that can control physical systems in IoT settings. So I'd like to stop here by thanking all my collaborators along the years, my students and postdocs here. Most of the work I showed you was their amazing work, as well as thanking our supporters from National Science Foundation and Northrop Grumman. And I would be happy to take your questions, as well as I hope hopefully next year we can meet in person and interact together, hopefully after this COVID-19 ends hopefully soon. So thank you everyone, and I'm looking for a fruitful discussion with every one of you. Thank you.